Hello everyone. Today we're going to be discussing ETAP's Intelligent Digital Substation, an application in different types of substations, such as renewable plants, industrial, transmission, and distribution networks. ETAP Intelligent Digital Substation is an integrated model-driven software and hardware system. It utilizes intelligent controllers and real-time operational digital twin to monitor, validate, optimize, predict, and manage electrical substations. Today we will be demonstrating ETAP's digital substation. We will start with the definition of a digital substation. We will move on to looking at the ETAP's intelligent substation capabilities. We will look at the intelligent substation automation functionality, cybersecurity, the applications of the digital twin in the digital substation world, and then we will conclude. The main definition of a digital substation is a system in electrical substation that interconnects the intelligent electronic devices. It then transfers the information to control centers and dispatch centers. There is a local HMI to perform manual controls and monitoring at the substation. The ETAP Intelligent Digital Substation goes beyond data acquisition, monitoring, and manual control. First, it uses ETAP's operational digital twin that allows validation of automation and operations. The digital twin provides complete details of the substation assets, which normally are not available in standard digital substation systems. This allows for quick decisions when locally performing work or operating the substation. Interoperability is important. ETAP IDS provides open communication architecture and integration, which allows for communication to third-party equipment. It also comes with full power management solutions integrated into the digital substation system. It provides automation and control capabilities. In a few minutes, we will see the programming and automation capabilities of the controllers. Understanding the conditions of the substation is very important for making decisions of operations. These features will help avoid critical incidents such as accidents due to exceeded component capacities or short circuit, as an example. The IDS system also allows you to predict system response before performing switching actions. It will identify switching sequence errors as well as potential overloads and other conditions caused by the execution of the SSM. Protection and safety validation is also included. This gives you a common platform that allows you to collect all the settings of all the different devices in the system in one common place. From there, you can do safety validations, you can check setting changes, you can look at historical logs, and get a complete picture of where the protection system is at the substation level. You can also access maintenance schedules and switching orders. The digital twin is the brain of the intelligent digital substation, starting from the design model of the network, going all the way to operations and automation. It provides the basis of advanced intelligent solutions included but not limited to predictive safety alerts. Before actions are taken, the IDS will provide alerts if a safety condition is predicted. Predictive alarms. In addition to the monitor alarms from the intelligent electronic devices, the system will actually monitor the component capacities and generate alarms when those are exceeded. This includes transformer overloads, bus under voltage conditions, and any other analytical alarm will be predicted and alarmed. Graphical sequence of operation. See on your diagram the operation steps before they are executed. It also provides a step-by-step validation tool of operation steps. It includes information of all the assets, including technical, maintenance, and more. The model also includes the protection settings with historical logs of changes performed in a single platform. The digital substation is run from the ETAP Intelligent Substation or ETAP Ice. This panel is included with the processors and controllers to manage the substation. It includes the data acquisition, processors, controllers, and cybersecurity components such as firewalls for a complete solution. The ISO features are hardware independent. It comes with a library of communication protocols allowing you for communications for third-party components. The IEDs can be communicated this way. Then direct control to circuit breakers is also available. It is IEC 61850 Substation Automation ready. All the components are also IEC 61850 Environmental Compliance ready. It also includes the digital twin model, server, and HMI application, power plant or microgrid controllers for renewable systems, grid compliance monitoring hardware, and all the components for cybersecurity for the entire system. In summary, all the hardware and apps for monitoring, automation, and control are provided for a complete solution. Let's compare common practice against ETAP solutions. In common practice, the manufacturer of the hardware provides the entire substation. The digital substation solution is then tied to that hardware. Adding any third-party component becomes a tedious job. In some cases, when taking an existing substation, the manufacturer may require you to replace all IEDs so communication can be done appropriately. In addition, there is no validation tools or intelligence built into it. With ETAP solution, you get a hardware-independent solution, so any third-party component hardware can communicate to the system. It has an open architecture and communications, integrated digital twin for advanced applications and management of the substation, automation-ready controllers with a lot of built-in functions already in place, and also with the programming capabilities to add additional functions. And in addition, you get grid compliance monitoring. The ISO also comes ready for remote communications. It can communicate to ISO and distributed energy resource management systems, receive set points, demand control signals, dispatch schedules. It also sends the necessary information such as loading and generation conditions. It uses DMP3, IEC 104, ICCP, and other communication protocols over secure channels to make sure security is maintained. Let's dive into the intelligent digital substation components. Let's start with the data acquisition. The data acquisition is performed via the ETAP Ice hardware. The ETAP Ice hardware comes with a collection of protocols and mediums of communications. The communication protocols include IEC 60870-104, DMP3, Modbus, IEC 61850, SNMP, Profibus, and directly from the processing server, it also includes OPC UA and ICCP for remote communications. The mediums of communication include serial RS-232, 422, and 485, Ethernet via fiber or CAT cable, radio communications, hardwired direct digital I/O and analog signals in 20 milliamps.
So what is ETAP Ice? ETAP Ice is a substation automation device that can be used for data acquisition and control. It has some different options in which it can be mounted, whether it's on a pole or whether it's on a field via DIN rail mounting. It can also be used as a front-end processor because the device can help to communicate to local devices that are either distributed on a substation or across multiple substations. And it offers the security to the user that the data will not be compromised using different solutions such as isolating networks, cybersecurity, and so on. This device also has the capability of enhancing or expanding the ETAP applications, such as intelligent load shedding. It can act as a controller for the solution, or it can act as a device for generation control, where it can communicate directly to the main ETAP server. There are different types of ETAP Ice models. Either it can be used as a compact device that can be either just purely monitoring devices via a local network, or it has the capability of it has a model that can be used to monitor hardwired signals in a substation, or it can be provided as a 19-inch rank complete one single device. Now let's look at the features that this device offers. So this device offers cybersecurity compliance. That means that gives you the security that either this device, in the case that it requires to connect to a network, it can communicate via, for example, a VPN network, so that it's in the same security level. You can also restrict the features depending on the users that are connected. This device offers different capabilities for cybersecurity to protect the integrity of the device as well as the data that is being transferred. This device is also, as we were saying, an automation controller. It's capable of supporting all of the IEC 61131-3 PLC automation standards. So this device can be used to create programs that can be used on the substation to perform different applications, such as protect device control, motor controlling, transformers, or even controlling an entire substation. You can create multiple programs and reuse them across projects on your ETAP Ice device. This device can also be used to connect to time synchronization. So in the given case, there's a time source device, such as a GPS clock. This device can synchronize the time source to on the CPU controller. The device includes multiple ports, depending on the configuration that you're using, whether they can be Ethernet ports or fiber optic ports. They support the routing, whether it's on a LAN network or a virtual LAN configuration, as well as a bridging or connectivity to VPN servers. This ensures that if you require to work on isolated networks, you can work and collect data locally at the ETAP Ice device and forward it to your ETAP SCADA without compromising security in your network. This device also offers redundancy. Redundancy works using either a network on your substation, a link on your substation network, or it can be used a dedicated synchronization channel. The dedicated synchronization channel allows for the two devices to be always in sync and also understand the state of each other. The redundancy feature also gives the capability of creating measurements that can be displayed on the ETAP HMI, where the operators or the system administrator can know the state of the devices and also be notified in the case that there is an alarm event going on that indicates that the redundancy process has started, so they can be notified right away. The device also offers different types of communication protocols. So the data going to the device, it can be used using like traditional protocols like Modbus, EMP3, IEC 61850, but it also includes an additional suite of protocols that this device can support either as a master or as a slave device. We have, in this case, the tool called ETAP Icon. That is the device configuration tool that you can use. So through this tool, you can take a look at your local devices that are directly connected to this device. So in this case, we're going to take a look into the software. So on the software, you can see, for example, I have my, this is a substation that I have a couple of devices that are connected via Modbus protocol. So each one of my devices, I can see it. I can see it. And also I can take a look at each one of the measurements that I am collecting from each one of the devices. So this is the data that is my device is collecting, and then the data that is forwarding to my ETAP SCADA. So all my forwarded data to my ETAP SCADA server, it's available also on this SCADA table. Now the interface of a single device or multiple devices directly into my ETAP SCADA server is going to be via my ETAP SCADA integrator database. So on my ETAP SCADA integrator database, this will allow me to monitor multiple ETAP Ice RTU or Ice Gateway devices across my network, and also monitor the state of all the measurements that I'm collecting. So in this case, when I'm working on my ETAP project, all I need to do is just create my single device, defining here what are going to be the measurements that I'm collecting from each one of my ETAP Ice devices. And then finally, we have the Substation Automation. So the objective of the Substation Automation is to provide an interface to the user where they can create programs using an IEC 61131 standard to define control on your substation. Now, the standard includes programming in one of the formats, which is ladder logic, but you can also create other programs like in text, function blocks, or any of the covered standards. So in this case, we're putting here a couple of examples of the programs. The device can handle multiple programs on the configuration. So in this case, we're looking into a configuration that is using protected device control, generation control, and also we're using it for other ETAP applications. The device, once it's online, you can view the data, and also you can display when you want to monitor the device locally for debugging purposes. You can view the state of each one of the measurements that are going along your device, just to determine when, in the case that you need to perform any type of maintenance on the device will give you the information about the measurements on that device is collecting, as well as the device. Just keep in note that the state of the device, as well as any alarm events, they are also forwarded directly to the ETAP SCADA. So the monitoring the device locally can be a very good tool to take a look into the device whenever there's an issue going on with the connectivity and how to troubleshoot it.
Now let's look at data visualization in the digital substation. ETAP provides you with a graphical user interface. When we see this interface, We have a easy to view navigation system that allows you to go to different parts of the substations or different substations depending on the connectivity and communication and access levels of your system. First, you can see the one-line diagram model here. This one-line diagram actually was exported or imported, I should say, from the ETAP from an ETAP model that was used for system analysis. So the program comes with a what we call the HMI Designer that allows you to import graphical one-line diagrams from the ETAP model. In addition to that, you can add additional components like gauges and other views. So for example, if I navigate to the home page of this system, we can see that in this particular ISUB system, we're monitoring 2 substations. We're actually bringing the data, real-time data, into here. We have the capability of adding gauges, adding trends, and any other graphical components to make the user interface more friendly for the operators. So if we go back to the substation, we can see the monitor, the status of the circuit breakers. We bring the analog information. This is all being collected from the ETAP Ice hardware and brought into the ETAP HMI. We also monitor the latest alarms and display here on the main diagram. We can go into more details and actually look at the metering details for the substation. We can see, for example, per phase measurements, voltage measurements, frequency, power factor, real reactive powers for each of the incomers and outgoing feeders. In this particular case, we're looking at a 11 kV, actually a 33 kV to 11 kV substation. Additional views can be created. As I mentioned, you have the ETAP HMI Designer, so you can create as many of these presentations as required. Notice that there is a lot of different configuration that is very flexible. Users, depending on their standards, can create templates that are designed to actually reflect the data. There's a lot of capabilities, including, for example, data quality. And in this particular case, for example, we see some measurements with a letter B, meaning bad quality of information, for example, coming in. So you can, the operator or the substation manager can easily see, what data is in good quality and bad quality. In addition to that, you can do a detailed alarm management on the system. So you can bring in a full management of the alarms. So from this alarm management, for example, you can come in here and actually say acknowledge alarms. You can do acknowledge selected. You can delete alarms. You can mute alarms. You can silence alarms. So you have a complete management of the alarm system here. We also have capabilities for unmanned substations where there is no operator, local operator in the substations. So we have features where there is automatic acknowledgement of alarms, although the alarm system is also sending this to the remote stations, SCADA systems information. One key factor to notice is in ETAP is this analytical alarms. This is very unique to ETAP software. So in addition to monitoring the status of circuit breakers and when they trip, you generate an alarm, or you look at set points. If there is a set point exceeded, we'll actually bring in that alarm into the system. But in addition to that, the system is also performing analytical alarms, which means that it's looking at the capacity of the transformers, and looking at the capacity of the feeder lines, looking at the voltage levels, at the bus levels. So if any of those components, for example, the capacity gets exceeded or the voltage goes above unacceptable levels or below acceptable levels, the software will generate its own alarms. So this is where the digital twin model becomes very important and very unique application in the system, because without the details of the capabilities of transformers, feeder cables, breakers, and so on, we wouldn't be able to create these alarms. So this is a very, very important feature, very unique to ETAP. In addition to that, you can have access to all the events. These events get recorded internally in the Ice subsystem in the processing server. We have capability of archiving and at least a month of information. Depending on the configuration of the system, what the requirements from the customer are, we can put in a local historian, or this information can get archived in an enterprise historian at the control center where all this information gets sent. So for example, here we can see some information like transformer overloads. We see a few status trips and so on and so forth. That all this information gets archived. The timestamp is the timestamp of the device. So which means that if we're using communications such as DMP3, IEC 61850, IEC 104, then we're getting the timestamp back from the actual device. That means the device that tripped the unit, or for example the relay, or the device that's monitoring the unit. So that information allows us to do a very detailed sequence of event analysis. The information here will include, for example, the components that get tripped. In many occasions, for example, if this was sent by a component protection signal, that information will also get recorded. So this, as I mentioned, gives you a very detailed historical view of what's going on in the substation. Then we go into the Tabular Dashboard. Tabular Dashboard is another view that allows the at the substation level to view all the signals in the system and actually be able to understand very quickly what is the status, what's open, what's closed, what's in good quality. For example, if there's communication failures, you can see them here right away. You can see all the measurements. This is automatically created. It's basically looking at the communication channels of the ETAP system, ETAP real-time server. So it's all that information is actually tabulated automatically. It's not you don't have to manually create this table. Now this information can be filter out. So if I wanted to have, for example, this, remember here we're looking at two substations. I can actually bring in here a substation column, for example, display it on my box, on my viewer, and then, for example, filter out anything that I don't want to see. So for example, if I only want to see substation 2, I can filter out anything else and look at substation 2. So it's a very nice tool to actually troubleshoot, to actually look at the system, see what's communicating, not communicating. So for example, here I see that there is a problem with one of the breakers. Another important tool that it's important to have at the substation is your service tags view. The service tag view, for example, gives you any tag out information that has been created on the system. So for example, here I can see that there is a maintenance, for example, a tag on transformer substation 2, transformer B, and I can see, for example, the notes that are being created either by the crews or are being created by the operator of the substation. So we can see here, for example, that at a certain time this was scheduled to be de-energized. The crew came on site, works got delayed, and so on. So every information for every these are the tags can be actually kept. All this information is kept in the historian, so you can go back and see what happened. Now, what this is also, there are different type of tag out. For example, this one is a maintenance, so it actually it's indicating that this transformer is a maintenance. There's control inhibition, for example. So if somebody is going to do work on the panel and you want to prevent any remote control, you can create a tag out called control inhibit, and that will prevent SCADA system to, or even from the ISO panel to actually send any remote control to actually open or close that device. So this is another tag in, tag out information that is very important in the substation level. And one more thing that's kind of nice is the report viewer. The report viewer is available in an enterprise solution. However, from the substation itself, I can come in here and actually look at and select all the reports here, for example, and go back and go to these systems and look at, for example, an energy summary, display the report, and I can get a very friendly Excel-based report with the different values, energy consumptions. If I wanted to, for example, get alarm reasons reports, so if there was an alarm and we want to know, for example, why the cause of the alarm, you will generate an alarm reason report. So the reports are historical, can be summary reports, they can be scheduled reports, they can be emailed directly from the iSub system. So it's a very nice tool to actually understand how the substation is behaving. So we're gonna look at other ways. So for example, the iSub system can also run the ETAP the system. So this is the ETAP model. For example, in this particular case, I go to the substation. Similarly to what we saw in the user interface in the HMI, we can actually see, for example, the data. We can see the real-time data. We can see some breakers with bad communication. Here is showing me there is bad communication. The white data is in good communication. So we can see really quickly the status of the system also within ETAP. The nice thing of having it in ETAP is that from here I have a full-fledged of modules, for example, switching sequence management. I have full management and service restoration. I have the low flow calculations, short circuit calculations, arc flash calculations, all of that available to me so where I can use real-time data and perform quick calculations. So over 100 modules that can utilize real-time data are available within the ETAP station. Another great application in the intelligent substation system of ETAP is the eProtect solution. The eProtect solution is has the capability of collecting all the relay settings from the devices. It has a built-in workflow, so you can go through the process of updating the different settings and have the capabilities of program or recommending the settings, have somebody else review them, have somebody else approve them. So it allows you to have a complete protection, visualization, and evaluation of the settings. So you have a central relay agnostic database. So that means that you can have many brands of devices, for example, in the substation, and then the eProtect will centralize that information and give you one common platform for viewing and updating if you like the settings of the protections. It is completely cyber secure, so it has different levels of security, including user access management. So not just anybody can go into the station and update settings. You have to have the right permissions to actually do that. It has the capabilities of health monitoring and maintenance, so you can see maintenance schedules. You can see the health of the devices. And also comes with or integrated with the automated fault analysis system. So it collects contract files, fault files basically from the system, and then based on that it can actually determine where the fault or the location of the fault is. So it gives you a complete centralized view of all the different protected devices, different brands, into one central location. You can communicate with the workstation and design analysis system. So you can actually, the ETAP analysis software can connect to the eProtect remotely. Again, having the right access levels and communication settings. And we'll get the information from the eProtect downloaded to ETAP. You'll be able to do your analysis of all the protection and evaluation of the protection schemes. And then the system will provide you with a light interface. It's a web-based interface that allows you to actually view and monitor all the different settings of the device. So let's look at that interface. So here we have a different 3 relays, for example, configured in this substation. You can you can communicate to other relays and devices from other substations as desired, and if you have the right permissions to do that. So in this case, we're looking at the 3 different relays. As you can see, as I click into the different relays, the relay settings, for example, this here, this information here is the different relay settings that were downloaded from the actual device. If I want to look at the history of this, for example, in this particular case, there's only one version of that information. If I go into this other device, if I look at that version, it looks like I only have one version here for each of those devices. So, but anyways, we have that the information. We have a log that will allow you to actually look at when the devices were updated, what settings were changed, and you will be able to actually compare. So, for example, if I wanted to change any of the settings here, if I have again the right permissions, I'm going to first save the current. Let me go into this relay here. It looks like I don't have the right permissions. So sorry about that, but I will be able to actually come in here, save the current configuration. Then I'm able to actually will allow me to go into make a change to the settings, and then send the settings to the device. So that means that from one central console within the substation, I will be able to actually make the setting changes from here. I can also download from the device. So if I went actually directly to a device, and with the manufacturer software, I made some changes to the settings, and then I want to download into the central location, I can do a on-demand download from the device. The eProtect can also periodically download or actually check if there's any updates on the device settings, and download those device settings as necessary. So from here, I also have the capability of sending it to ETAP. So if I wanted to send this information into the ETAP software, I can actually click on a button and send that information to the ETAP model, and be able to do the relay protection, the relay coordination and settings studies with this information from the ETAP eProtect. So this is just a quick summary of the eProtect. It's a very important feature. Again, it's device agnostic, so you can get different manufacturers, different brands, communicate it to the ETAP substation, digital substation, download the information, and centralize the settings, and having very quickly available when you get into the substation. So it simplifies the data collection whenever you're going to do system studies. So again, if you're using ETAP for system analysis, you can, with a click of a button, you can actually take these settings and send them into your ETAP model, and save time and save money in short. Now let's look at a quick demo of the automated fault analysis system, AFAST.
The AFAST product allows for the analysis of ComTrade files for multiple different relays to help properly locate where a fault might be. For example, on the top portion of this one-line diagram, we have 2 substations, one here, and transmission network, transmission lines in between. If I zoom in to one of these substations, here we can see a number of relays in that feeding that transmission line. There's also a lot more relays in that same transmission substation. Additionally, on the other side, if I zoom into this network, here I can see another set of relays that are defined on that transmission line, and then again, another transmission line with its own set of relays. So we have a number of different relays feeding a number of different lines in that substation. The beauty here is we can take as many relay Comtrade files from the system and correctly assign the fault location. So in this example, I'm going to pull up our AFAST viewer. So here I have an incident. This is incident number 43, which happened on this date. And we've received all of these Comtrade files for these relays. So we have, say, 10 or so Comtrade files, but most of these Comtrade files don't have faults specifically associated with them, only a couple. So here on the fault location section associated with that incident 43, we can see a number of different calculations for that fault. So as we use different algorithms, so here we can see there's a number of different algorithms, single end reactance, single end Takagi, etc. We can use that information to get a very precise estimate of where the fault is located. So for instance, this fault was started at this node, ended at this node, and was on this cable with at roughly 0.46 kilometers away. You can see each of these different calculations has roughly the same value, but if we use multi-end, we have a very accurate location, about 23% down the line. Now, additionally, we can use the thin waveform viewer to visualize the various waveforms. So this isn't as advanced as the application waveform viewer shown previously, but this is a way to very quickly see all of the faults in the system and have a view of all the Comtrade files. Now, once we have that analysis, we can see the AFAST results on the geospatial view as well. So if I execute, show all of my historical AFAST views, now I can highlight and see here are all of my incidents that my fault locations that I've predicted in the system. So the AFAST provides for a calculation on where a fault may be using multiple different methods, as well as visualization of the waveforms, and finally, visualization of the fault location on the geospatial map.
Now let's look at the intelligent controllers that can be integrated in the digital substation. We start with the power plant controller. The power plant controller is designed to coordinate the inverters, battery storage, management systems, stock comps, and other devices within the power plant to make the system grid code compliant. It acts as the central plant monitoring and supervisory control of the solar power plant. Another controller is the microgrid controller. The microgrid controller performs generation dispatch, black start management, islanding, and reconnection management of the microgrid. Using the digital twin model, the controller can be validated in ETAP as well as performance of the microgrid, and then logic downloaded to the microgrid controller, performing software in the loop and hardware in the loop testing within the same system. Another controller is the Intelligent Distribution Load Shedding controller. The IDLS controller solution uses the digital twin model, real-time data, load priorities, and system disturbance to shed the best combination of loads to meet the required load and optimize quality of service. And last but not least is the dynamic system monitoring. This device performs the digital fault recording, dynamic swing recording, sequence of event recording, power quality recording, long-term recording, continuous disturbance recording, and real-time phaser monitoring in the system. Let's look at the configuration and settings of this device.
The Tesla control panel is the tool used to configure and visualize various data from a Tesla device. Here we have the Tesla control panel software. First, I'm going to start by connecting to my device. So this is making a TCP/IP connection to the unit in the field. The Tesla device utilizes role-based authentication, so I'm going to go in as service access, which is the highest level of service, and there's no credentials set up for this device. Here I can go through and look at my settings first. So here I'm going to go to my present settings, and I'm going to get those settings from the IED, and I can download a setting here. And then I can double click those settings to see the actual details of those settings. So here I can set up my limits for my various parameters, set up alarm signals, so I generate alarm signals based on various issues, as well as navigate to my DNP configuration, look at my class data, look at my DNP mapping. So this is if you have a SCADA, if you use ETAP real-time, to communicate to the device, you can set all that up here and then do the point mapping within the ETAP real-time environment. Additionally, moving on to the channel section, here we can define all of the different CTs and PTs, basically the devices or the measurement points that we're measuring by this fault recorder. So here I have set up a number of different points where I've defined the different measurements, as well, both inputs, so hard inputs, CTs and PTs, and the derived inputs, calculated values, so the megawatts, megavars, etc. So all of that is calculated in here. Additionally, in the trend section, you can define what measurements you'd like to trend and make available for a ComTrade file. Here you can define what measurements are used for the PMU data. So what do we want on our phaser data available? Finally, the CDR is our continuous disturbance recording capability, where we can continuously create those ComTrade type files and make that available on a running basis. So next, I'm going to leave the settings mode and go back to my main mode. That here, and look at the various data. So here I can look at my records. So I'm going to go to an existing fault on the device and open the record graph. So here are my my measure data, my analog measure data here. So I can go through different measurements and see during this ComTrade, during this fault, the measure data. Here I can look at external data, so the inputs and outputs, the circuit breaker positions. Additionally, I can look at my calculated data, so my negative sequence, for instance, of my voltage. These are calculated by the Tesla device in the field and stored in the local memory for that device, as well as the positive sequence measurements, or calculated values, the zero sequence, and then also the power. So you only have CTs and PTs, but here we're calculating the actual power on the fly for various channels. Next, I will move to the trends. Here we can actually do real-time trends of data and events. These are sequence of events. So for instance, when a circuit breaker trips or a value goes past its thresholds, we'll generate an event here. And these events can be passed to the master via DNP as an SOE, IEC 62150, etc. So all of these events are available internally in the device, as well as available to the SCADA system. Next is the metering. In the metering section, we can see real-time data in the field. So here's the actual measured data on the device. So this is feeder 2, showing the actual current magnitudes, the calculated watts, etc. Additionally, we have our statuses from the device. So these are all of the different statuses, the calculated harmonics, not much here, and And finally, the PMU phaser data. So this is that very fast phaser data available. So all of this is available within the Tesla control panel, as well as available to the SCADA system for ETAP real-time. Finally, there's the continuous recording capability, where we can continuously record and create a Comtrade file on the fly. The Waveform Viewer is a very powerful tool which is used to visualize and run calculations against a Comtrade file or other waveform data. So here I have one waveform file which I've already loaded with a number of different signals. We can load existing files that have been downloaded from the ETAP drivers that are capable of downloading Comtrade files, or we can ad hoc add a new file. So here I'm just going to select this DAT file, and now it's available as in my list of signals. As with any tool for waveform analysis, the standard panning and zooming capabilities are there. We have a time bar, which allows us to calculate the time difference between various events. So here's when the event happened, and you can see that's about 100 milliseconds of recording time for that event. Additionally, we can bring in new measurements. So here we have all of our instantaneous measurements here. So these are all the instantaneous measurements calculated, as well as RMS values. So for instance, I'm going to bring in my B phase RMS value into that view. I'm going to change the color to make it more obvious to yellow and hit apply. And now you can see the RMS value here for that B phase. So my B phase RMS value based off of my B phase instantaneous current. Additionally, we can bring in many other different calculated values. For instance, phasor values, my positive, negative, zero sequence data, my frequency information. I'm going to bring in my harmonics here to my harmonics page here, and just bring in my DC second and third order harmonics and apply those. And here we can see my my harmonics data here. So I can zoom in and see that this is where the harmonics information is available. Additionally, we can add new trends. So I'm going to add a new view, and I'm going to call it I'm going to put it right here, and I'm going to populate it with power data. So I'm going to select that new chart, rename it to power, and then bring in my calculated power data. So for instance, my total P, my positive, negative, and zero sequence data. And I'm going to hit apply, and now this data, these signals, are available in this trend here. So here we can see my total power, my positive, negative, and zero sequence data as well is all available in this screen here. Additionally, there's a lot of configuration that can be done. So for instance, I can bring in my styles, change my precision, change my, let's say, my thickness of my lines. I can change the background color, all of this, and it's theme based, so I can bring in different themes as well. So I can have a look and feel that I want. And then of course I can save all of this into one package.
We have covered many capabilities of the ETAP Intelligent Substation. We learned that the ETAP Intelligent Substation allows us to control and automate of power plant, distribution, transmission, and industrial substations. It comes with an integrated digital twin applications that allows us to analyze and make better decisions when operating the substation. It comes with an integrated intelligent controllers that allows us to optimize the operation of each substation. And also it's integrated with operation and visualization of the entire system. The intelligent substation of ETAP, intelligent digital substation of ETAP, is a hardware agnostic, so we can connect it to any third-party devices with the standard communication protocols such as the IEC 61850, Modbus, the MP3, and others. Many of the intelligent controllers that we talked today, we have created webinars. Please look at our website to view those webinars in detail. Thank you.